Okay, should be recording. So as you guys know, I always like to start with like a meme or a cartoon or something like that that just reminds us of what it is that we're doing in Mech 2, and again tries to shift the perspective from kind of the engineered centered experience that you guys have had up until now to a user or customer centered experience. And this is yet another one of those examples where you can sort of see what's going on here. The sign is meant to keep bicyclists safe, and yet whoever placed it here placed it in a way that puts them at greater risk. And so yet another design fail. Anyway, I'll let you guys ponder that for a second here as I transition to the next slide, which is there. Okay, so we've now finished the tolerance loop module, and we're transitioning into actually a very short module. It's just one lecture on insertion and handling time, and this is another kind of element of design and mechanical engineering that you don't really get anywhere else in the curriculum. And so we thought it important to include it, particularly because you could use this, for example, in the reverse engineering report as for like a DML analysis. So the thing that I wanted to mention to everybody before I jump into the slides, if you've got your artifact with you, your RER artifact with you, now would be a good time to try to like take it apart. So like, pull the pieces apart, get all the O-rings off, pull the gasket out so that it's, let's see, 6 separate parts, because a few slides in, I'm going to have you guys put it back together and time yourselves doing that. And then we'll use that data as at least one potential analysis for the RER. So, but it sometimes takes students 5 or 6 minutes to get their artifacts taken apart, and that's burning through class time. So take it apart in the background while I'm chatting here. So this is the plan for what I want to talk about today. The first topic is what exactly is this assembly time thing that I speak of? So let's jump into that. So if you guys go out, on the internet and you look for like, advanced manufacturing techniques, you'll find that there's lots of pictures and videos of like robots doing assembly. Typically auto manufacturers use robots to do most of their assembly. So you sort of get this erroneous impression that everything is put together by robots these days. And it turns out that's not true. Most products produced in the world today are still assembled by hand by people called assemblers, and it turns out that assembler labor typically constitutes the bulk of production costs for most products, and so this, to some extent, explains the migration of manufacturing jobs from the U.S. To other countries abroad, because the cost of labor is less in a lot of those other countries. So the goal then of a design engineer, given that labor is time and time is money, is to try to figure out 2 things. So one is the fastest sequence to follow to assemble a bunch of parts into a finished product. And once you have that fastest time, then you want to be able to estimate for costing purposes what the duration of that time is, right? With the goal of basically having it be as short as possible, because that drives down cost. So there is a technique to do this, and the technique was generated by two guys who were originally professors in Pennsylvania. So these guys named Boothroyd and Dewhurst, and they were so successful with this assembly time estimation technique that they no longer work for the university. They actually now own a private consulting firm called Boothroyd and Dewhurst, where they basically consult for companies on how to improve their assembly time for products made by those companies. So this is a technique that's used quite often in industry now, because these guys now run a company that does it. But basically, what they did to generate these estimated assembly times is they went out and they watched a whole bunch of different assemblers in different parts of the different parts of the country, different times of day, different industries over a wide period of time, just assembling, every, manufactured widget that you could possibly imagine. And they collected all of this data, and then they synthesized all that collected data into a series of charts, where the charts represent how much time it takes to do an individual process in an overall set of assembly steps. So so-called Boothroyd and Dewhurst assembly time is basically made up of two different charts, and you're not really meant to see the words or the pictures or the numbers on these charts, more so that I just want you to see that there's two different charts, and each one of those charts represents one kind of isolated step in an assembly process. When you think about it, when assembly is done, every part really needs to be treated two different times. So once is the assembler actually has to reach out and grab the part. That process is called handling, and that includes grasping the part and then also orienting the part correctly so that it can be inserted into the subassembly. And then the second thing that happens for each part is the actual insertion and securing that part in the subassembly so it doesn't fall out. So that sort of combination of steps is called the insertion process. And so we have a handling chart and we have an insertion chart. And so that's sort of the big differentiation between these two things, is there's a chart for each one, handling and insertion. And ultimately you'll get to a point where you do a handling step and an insertion step, and a handling step and insertion step, a handling step and an insertion step. And you'll refer back and forth between the handling chart and the insertion chart, depending on which one of those steps that you're in, using those charts to look up a value for the time estimated that it takes to do whatever it is that particular process is. And then you sum up all of those times, and that sum of times is the total assembly time for that product. So that's basically how this works and where we're going. So this is point number one, is that there's two different charts. These are a couple of additional guidelines. So the second guideline is when you look at the charts in detail, you'll notice that there are certain numbers that seem like really high for what the process is. So the one that I kind of fixate on is the flip process. So a flip process, according to the Boothroyd and Dewhurst charts, it takes 9 seconds. And it's like, how long does it take to just flip something over from front to back? There's no way it takes 9 seconds, but Boothroyd and Dewhurst is it listed as 9 seconds. So your kind of intuition might be, well, I'm trying to get the cost of this thing down. And so I'm going to artificially go in and reduce the numbers so that a flip doesn't take 9 seconds, but a flip takes like 2 seconds, right? Because intuitively, that's really what it should be. So my kind of admonition, my warning to you is please don't do that. Please just apply the values from the chart, following the original intent of the researchers. And there's a couple of reasons for this. So one, again, these guys observed literally tens of thousands of assemblers like doing these processes over and over and over again. And these numbers represent like an aggregate value across all those different observations for that particular process. So it is, statistically pretty accurate. And then also, at least for sort of initial costing purposes, it's always better to overestimate rather than underestimate, right? If you overestimate, you can always go in and refine your estimation later when you move into the actual assembly process. Whereas if you underestimate and develop like a product cost based on an assembly time estimation that's too short, your product is going to end up being, not priced correctly, and then you have to increase the price, which of course upsets the customer. So better to over predict rather than under predict. So the third kind of guideline point here is that these numbers represent a baseline of assemblers basically doing the same repetitive task over and over and over again for 8 hours a day for 5 days a week, right? That's literally what assemblers do. They assemble things for a living. And so you might feel like and in fact, we're going to do this in a second, which is why I'm asking you to take your RER artifacts apart. You guys are going to put your RER artifacts back together, and you're going to time yourselves doing that. And you might say to yourself, well, I've calculated this Boothroyd and Dewhurst assembly time, and it's like ridiculously long, right? Like I can put mine together in 2/3 of the time. So why not just use my number rather than the Boothroyd number? Well, it's because you just did it once, right? So if you think about somebody doing the exact same repetitive task over and over again for 8 hours, they get into sort of a rhythm, a cadence. They're not necessarily going as fast as they possibly can. They're going at a pace that allows them to, continue working without getting exhausted, without some sort of repetitive strain injury, for these long periods of time. So I can speak to this from firsthand experience. When I ran my company, we one time got a really big order that the customer needed like pretty soon, and I didn't have enough assemblers to actually meet the deadline, and so I had to go down. I was the CEO of the company. I had to go down and actually get on the assembly line with the assemblers and like do the assembly with them, just to be an extra person on the assembly line to speed things up. And oh my God, after 8 hours of doing the same thing over and over and over again, like you're in a lot of pain. It actually takes quite a while for the human body to sort of build up the resilience to be able to do the same repetitive task over and over again for 8 hours. So these numbers again represent a baseline for somebody that is basically doing the same thing over and over again for 8 hours. So they're not necessarily going to do it as fast as if you did it one time. Now, on the flip side, if you've got somebody doing something over and over and over again, they get progressively better at it, right? So the more times they practice it, the more times they do it, they find little tricks and little cheats to do things faster. So there's two sort of competing factors. One is your assemblers become better at assembling as they gain more experience, but also the longer that you have them assemble things, the slower they tend to go. So those two competing factors are basically captured in the tables, because again, the tables sort of represent this statistical average of assembling things over a long period of time. Lots of observations. So that's point number 3. And then point number 4 is that the charts remind us that there are trivial processes, at least processes that we think of as trivial, that actually do take time. They're non-zero time tasks. So things like reaching out to grab a part from a bin, things like grabbing a screwdriver or need a tool to do an insertion, or just reorienting an assembly because you need to access the back side of it, for example. In our daily experience, those processes happen, nearly instantaneously, half a second, something like that, right? And you probably wouldn't consider including them unless the charts kind of reminded you to. But if you think about it, if you're an assembler and you've got, maybe a part or a subassembly reorientation that takes half a second, but you're doing 10,000 of those flips, right? Those reorientations, that's 50,000 seconds, which is a good number of minutes and a good number of hours. And those hours then translate into the extra labor time. So it is really important to capture every single step and every single process that the assemblers have to do, even if, from your perspective, those things seem trivial, because they do take some non-zero amount of time that has to be accounted for. Okay, so any questions then about like what assembly time is, or sort of those basic guidelines for how to use the charts? Nope. Okay, I think we're okay. Oh, there's a question in chat. Oh, no. Okay, somebody just says all good in chat. Okay, awesome. All right. So hopefully I've given you enough time to take your hose nozzles apart, all the way down to freeing up the O-rings and pulling the gasket out, because now I'd like you guys to go through the experience of what it feels like to reassemble a product from its individual constitutive parts with a little bit of urgency, right? So, not just sort of lazily doing it, but doing it knowing that you're being timed. So what I'd like to ask you guys to do, if I get to the next slide, there we go, is to grab your artifact, make sure that it's completely disassembled into all of its 6 constitutive parts. And you can use a stopwatch or a cell phone or whatever you want to time this. But what I want you to do is just put all the parts in a pile and then time yourself Uh-oh, somebody has 7. Oh, you might have 2 gaskets.
Yeah, there's 2 gaskets there on the bottom where it threads onto the hose. So I assume just use one.
Yeah, just use one. The second one is a replacement, which actually that's sort of interesting because all of the hose nozzles came with 2 gaskets. And so in a way, that's sort of a message from the manufacturer telling us where they think the first failure mode is going to be. So if you guys are doing like a Mech 1 type analysis, probably good to focus on that gasket because the manufacturer gave us 2 for a reason. It's because that's where they think it's going to fail. But yeah, it's meant to just have a single gasket. So just assemble it with 1 rather than 2. But time yourself doing that. And then when you guys are done, if you just drop your assembly times into the chat here, I will record them. And what I've done is I've taken data from the 935 section and the 155 section. I'll add your data on top of that. And then you guys will be able to then have like an average assembly time over like 50 or 60 people. And if you wanted to, you could do like a DML type analysis for the reverse engineering report, where you compare the Boothroyd and Dewhurst assembly time that you calculate to the actual assembly time of a group of your peers, putting the same artifact together as the one that you've analyzed in the Boothroyd and Dewhurst technique to see how accurate it is, right? Is Boothroyd and Dewhurst giving you an over prediction or an under prediction, and why? That would be, a very interesting DML type analysis. So we'll give you guys a second to do this, to reassemble your artifacts, time yourselves doing it, record the assembly time, and then just post your numbers into chat there. And then once you guys have done that, we can move on. So any questions about what I'd like you guys to do? No, I think you're good. Okay. So go ahead and time yourselves putting your hose nozzles back together. And when you're done, just drop those numbers in chat. I'll give you guys about a minute or 2 to do this. And then once you've had that experience, we can move on with the lecture. We just set a clock here so I know what time it is. Okay, so we'll give you guys about 2 minutes from now. All right, that's about 2 minutes. Okay. Okay, so we've got it looks like a minute and 51 seconds. I'm just going to read this if that's okay. I'm going to be honest. I couldn't get my O-rings off without breaking a nail. I can email results later. Yeah, no problem.
Yeah, I had to use tools to get it off. I couldn't get it off by hand either. I used a dental pick.
Yeah, there you go. Yeah, so in class today, I actually handed out like thumbtacks, and had students use a thumbtack to sort of dig under it to get it out. Still trying to get it off. Oh boy. Okay, well, we got one time.
Flathead works if you have that. I've done it with that.
Yeah. That'll
It
work.
wasn't
Okay.
easy though.
Yeah, no, it's we had in class today, we had people like O-rings were flying all over the place, and a bunch of people broke their O-rings trying to get them off and stuff. So anyway, yeah. So if you guys want to do this sort of offline and then email me the numbers or text me in Teams the numbers, that's fine too. But at least the one number that we got is 1 minute and 51 seconds. So which is pretty consistent with kind of the average that I saw across the other two sections. So, okay. Anyway, hopefully that was a little bit fun, at least trying to fight the O-rings and get them off. All right, so let's move on. Now that you've at least had the sort of the experience of reassembling. So let's walk now through the actual booth ready Dewhurst assembly time process. So, and again, I know that you guys probably can't see the words or the numbers, and I'm going to blow this up later so that you guys can see kind of what some of the words and numbers mean. But this is more about navigating like the overall chart. So, so the first thing that we want to do in estimating the assembly time is think about like the sequence, and for the very first part the assembler has to reach out and pick that part up. So that's the first handling step. So we're going to go to the handling chart. So see here it says manual handling estimated time. So the keyword there's handling. This is the handling chart. The first question that you want to ask is how many hands am I using and why? So you have 4 subcharts. The first one is for a one-handed grasp. The second one is one-handed grasp with grasping aids, so something like pliers or tweezers. The third one is 2 hands for part manipulation. And then the third one is 2 hands or assistance from like another person required for large part size. So if you got something that's so big that it's unwieldy enough that you can't hold it with one hand, then that's what the last one is for. So that's the first one is how the part is grasped. And then once you've determined how the part is grasped, then the second thing is to calculate the sum of the so-called symmetry angles. And you need the sum of the symmetry angles for the first subtable. You need the symmetry angles separately for the second subtable, and then you don't need them if you're in the third or the fourth subtable. But for the most part, at least in the size of parts that we're going to deal with in Mech 2, you're going to be either grappling or grasping with one hand or one hand with aids. So you're probably going to be in like the top 2 of these subtables. And so good to know what these symmetry angles are. So here's the formal definition. No need to like read these in gory detail. I have a 2-minute war story here, which is so this is the formal definition, and then this is my definition. And you guys probably know Professor Griffiths. He's the undergrad coordinator. And so every so often, Mike, Professor Griffiths will pop into one of our lectures, just to kind of critique us, right, and give us some feedback on how well we're doing. And like this is his area of expertise. He is like an assembly time god. He knows everything there is to know about Boothroyd and Dewhurst. And I'm an energy thermal fluids guy. I like this stuff. I find it interesting, but I have nowhere near the level of expertise that Professor Griffiths has. And so I'm giving this lecture, and he happens to walk in like in the Boothroyd and Dewhurst lecture that I'm giving, and I'm like, oh my god, I'm gonna die. Like he's gonna fire me on the spot. This is terrible. So he's a nice guy, and he didn't do that. But what he did say, which I understand understand and respect is my approach has some holes in it, which I admit that it does. I'm actually going to give you an example in just a second. And so what his recommendation is to just show you guys that there is kind of a formal definition for what all these things are. And that definition is here. And if you guys get stuck with my definition, my way of doing it, which my way is right about 9 times out of 10. But you might run into a situation where it seems like there's 2 right answers, which again, I'll give you an example in a second. Then the suggestion is to go to the formal definition, which is here, of all of these symmetry angles and thicknesses and size. But if you can use my way, I think it's a bit better, just in terms of understanding. But you could use the formal way that Professor Griffiths advocates, if my way ends up giving you some sort of paradoxical result. So anyway, so this is here, just in case you need it. But to me, this is like really hard to understand. So I've got my own version of it. So the example that I give is of a paper clip, and the reason that I choose a paper clip is because I'm hopeful that everybody in the lecture has used a paper clip. And you're familiar with the fact that paper clips have some directionality, some insertion directionality to them, right? So if you come in from the way that I've got this thing oriented, from the right side to try to clip a stack of paper together, that's the way that the paper clip wants to engage with the paper, is insertion from the right side here. If you try to insert the paper on the left side, you're gonna run into these sort of wire ends, these flat wire ends, and the paper won't go, right? So there's a very clear kind of directionality associated with paper clips, which hopefully everybody has experienced accidentally trying to put a paper clip on backwards and not having it work. So that's why I use this. Okay, so let's start with alpha, the alpha symmetry angle. And so this one's a little nuanced. It's kind of the hardest one to understand. But I'll walk you guys through it, and hopefully we'll be able to get it. So this alpha angle is the angle required to repeat an orientation about an axis that's both perpendicular to the insertion direction and normal to an insertion part adjoining face, is basically what that means. So like sort of hard to parse, right? There's an awful lot of information in that sentence, but basically what it means is, if you think about the direction of insertion, it's along this long red dotted line here that's basically running down the center of the paper clip from the back side to the front side of the paper clip. So that's the direction of insertion. You're going to insert this thing to your right, onto your stack of paper. The axis around which the alpha angle is measured is the angle is the axis that's basically coming out of the page towards us, right? And I couldn't represent that super well because this is a flat, flat image, but it's basically rotation of the paper clip around the axis that's coming out of the screen towards us, right? So I wonder if I can I grab it? Oh, yeah, I can. So it's like rotation of the paper clip like this way is rotation in alpha. I couldn't do that in the other sections. There we go. Okay, so that's an alpha rotation. So it's both perpendicular to the insertion direction, and then it's also a rotation about an axis that's normal to an insertion insertion adjoining face. And so what I mean by insertion adjoining face is when you slide the paper onto the paper clip, it's basically this face here that we're looking at that's adjoining the surface of the paper. And so we're looking for an axis that's normal to that surface. So again, it's the axis that's coming out of the paper clip towards us, is the axis that we're rotating around for alpha. So that's that one. Beta is much easier, I think, much more intuitive. Once you get the insertion direction figured out, beta is just a rotation around that axis. So it would be like if I were to just turn this paper clip over, right? If I were to just flip it over, like flipping a pancake, right? That would be a rotation around the beta axis. So those two are require a little bit of kind of visualization. The other two measurements that you need, I think, are a bit more intuitive. So thickness is the dimension of the shortest side, but really it's the dimension that your picking up the part with, right? So here the paperclip is laying flat on the table and you're picking it up and your fingers are engaging with a thickness that's basically the diameter of the wire that the paperclip is made out of. Now, in a way that this is sort of subjective, especially for us, because for me, when I did this insertion process for our RER artifact, my natural tendency was to pick up this part on the left, kind of the internal nozzle, not from the wide area of the base here, but from the narrow, the narrower area, kind of inside the nozzle. So thickness is really where you sort of naturally grasp the part to pick it up, is where the thickness comes from. And again, it's a little subjective about, where your assemblers would actually grab this thing. But that's thickness. And then the last one is size. So size is just the length of the longest side, which in this case is just the, the full length of the paperclip is S. Okay, so any questions about any of these definitions before we move on? I'm going to do like an example to kind of walk you guys through, but I want to make sure that you at least have a sense of what these things are. No, I think we're good. Okay, all right. So here's a couple of examples. So I give just a series of sort of simple shapes that are meant to be inserted into holes in a flat piece. And the simplest example is the sphere. So it doesn't matter what orientation the sphere is, and think of like a marble going through a circular hole, provided the hole is a bigger diameter than the marble, it doesn't matter what its orientation is. And so it's an alpha 0 and a beta 0. The next more complicated one is a cylinder. So like a right cylinder going through a circular hole. And so this guy has an alpha angle of 180 and a beta angle of 0. So 180 might seem, kind of like, why 180? It's lined up perfectly to go through the hole right now. Why would you, flip it 180 degrees? So the reason for that is it's actually this word right here. So it's the angle to repeat an orientation about an axis perpendicular to the insertion. So for us, alpha in this case, or at least the axis around which alpha rotates, is coming out of the page towards us, right? So if I were to rotate this guy in alpha, I'm going to rotate the whole picture. I would rotate it like that, right? That's a alpha rotation. But around like this axis, right? An axis that's coming out of the center of this thing. And right now it's lined up perfectly. And so the question that I'm asking with these angles of symmetry is, if it's lined up perfectly, how far do I have to rotate it so that it will again fit through the hole with all the same features, or all the important features, in the same orientation that they're already in, right? This thing is basically symmetrical top to bottom. So if I flip it 180 degrees around alpha, it'll still go through the hole, and there are no key features that have to be kind of pointed in any one direction. So that's where 180 comes from. And then beta equals 0 is a rotation around the long axis of this cylinder. And again, it doesn't matter where I rotate it, it's always going to fit through that hole. So that beta angle is 0. This one I'm going to leave you guys to figure out. This one is a situation where my version of things breaks down, and we have to go back to the more sophisticated language in the textbook. So I'm going to leave that to the next slide where I explain that one. The one that I want to kind of finish on with this slide is this one, which looks like a bolt, right? So pretty standard mechanical engineering part. And this one is an alpha 360 and a beta 0. So alpha 360, because if you've got a bolt and it has a head on it, if I rotate this guy just 180 degrees, I'm now trying to shove the bigger head through the circular hole. And it won't go, right? So you have to rotate this guy all the way around 360 degrees in alpha to get it back into an orientation where it'll go through the hole. So that's why it's 360. And then beta might seem a little counterintuitive, because if you've ever had an experience of trying to like thread like a machine screw into a hole, a lot of times the threads don't line up correctly, right? And you actually have to like turn the thread a little bit to get the thread to engage. And so it seems like for like a thread going into a hole, that this number should be, something bigger than 0. It should be like 10 or 15 or something like that, to account for how far you have to turn to get the threads to engage. So yes, that intuitively is correct. But remember, we've got both insertion, both handling charts and insertion charts, and the handling chart only accounts for the amount of time that it takes to pick up the part and sort of get it oriented correctly in preparation for insertion. And then the insertion is actually like screwing the part in or shoving the part into the hole to its final location. And so the reason that this beta is 0, even though kind of in your experience you sometimes have to rotate a bolt to get it to engage, that rotation is accounted for in the insertion part of this overall process. So long as you get it aligned to go in the hole, you're good, and beta is 0, and you have to account for the time that it takes to rotate it in the insertion step, not in the handling step. So that's why this is the way it is. Okay, so any questions about these shapes, with the exception of this one, which I'm going to talk about in a second, and why their numbers are what they are? Okay, I think everybody's good. Okay, so invariably, like I said, my technique breaks down in certain situations, and this is one of them. So I mentioned, we're looking for an angle to repeat an orientation about an axis perpendicular to the insertion direction and normal to an insertion adjoining face. And so using that definition, if this part is being inserted downwards, the axis around which alpha rotates could either come out of the square shaped face, or equally valid in that it could come out of the rectangular shaped face, which I call alpha prime. And both of those are correct, right? Based on my definition. And to make matters worse, they have different alpha angles, right? So the alpha of this guy is 90 degrees because every time you rotate it 90 degrees, another one of these rectangular faces is aligned downwards, and you could drop this thing through the rectangular hole. Whereas if I rotate this guy 90 degrees in alpha prime, it's now this big fat square face that's facing downwards, and that big square face isn't going to go through this much thinner rectangular hole. So this guy actually has an alpha prime of 180. So that seems to be like a paradox, right? How can these both be right? So it turns out then that there's kind of a more subtle analysis that you have to do here, which is wrapped up in like this definition out of the textbook, which is you've got to number the faces. So if you run into a paradox like this, you have to go to the more sophisticated definition. And so what we'll do here is we'll number the faces. So the square faces, which are symmetrical, get numbers 1 and 2, and then all the rectangular faces get numbered 3, 4, 5, and 6. And then you're looking for let's see, insertion. You're looking for an axis normal to an insertion adjoining face, but then you also want to pick the angle of symmetry that is the lowest in this case. And so here we're looking at how like face 1 interfaces with this longer edge, right? I've got a little note here that say faces 1 or 2 can go along this edge, and faces 3, 4, 5, and 6 can go along this edge. And so because this orientation gives you a lower value of alpha than this orientation does, you always want to pick the lower value. And that's how the Boothroyd and Dewhurst charts are set up. And so it's this direction for the axis around which alpha rotates that we end up selecting by kind of using this numbering approach and looking at which one of those orientations gives us the lowest alpha angle. So hopefully that makes sense, but let me pause and ask if anyone has questions about, kind of how to resolve this paradox if it occurs. Nope. Okay. I think everybody's okay with that one. Okay. Sometimes that trips people up, but I either did a really good job of explaining it or everybody's asleep. So hopefully it's the former, not the latter. So, this should be red. Let me just change that. There we go. Okay. Okay, so once we get the symmetry angles sorted out, then we go to the top and we have to decide whether the parts are easy to manipulate or difficult to manipulate. What defines difficult to manipulate is encompassed in this little sub footnote here, right? So number one takes us down here. So parts can present handling difficulties if they nest or tangle, stick together because of magnetic forces or grease coating, and so on, are slippery or require careful handling. Parts that nest or tangle are those that interlock when in bulk, but can be separated by simple manipulation of a single part. So there's a big long definition, but basically anything that's kind of that presents a problem when you grab it is a part that presents handling difficulties. So it's a little bit subjective. You guys will see, provided we have time. I've characterized our O-rings as difficult to handle because they've got oil on them, and so they're very slippery. So first you make that determination, and then you use your thickness and your size to determine how you sort of traverse. It's sort of like a game of Plinko, right? You traverse down these columns based on whether the thickness is greater than or less than 2 millimeters, and whether the size is greater than 15, between 15 and 6, or less than 6 millimeters. And then you hit upon a particular column, and where the column that you've selected and the row that came out of those sum of the symmetry angles align, that's the number that's associated with the time in seconds for that particular operation. So we've got just a couple minutes left. And so I want to just walk through like one example to kind of show you how this works. We did start about 5 minutes late, so I might go a minute or two over, but so we have here a template, an assembly time template, and all of this, except for the handling and insertion code, which I'll explain in a second. So the step number, the handling or insertion process, alpha angle, beta angle, some of those angles, the HI code, and then the process time. So our goal is to fill out each of these rows, and ultimately each one of those rows is going to have a process time associated with one step in our overall assembly scheme, and then we're going to add up all those process times, and that's going to be the total time to assemble the product. So that's the direction we're going. So the example that I'll give is for those of you that managed to get your sub-assemblies apart, is to place one of these larger O-rings onto the inner nozzle component here. So how do I do that? Well, I've got to take a couple of measurements. And in fact, here, let me move this down here. There we go. That makes more sense. So I've got to determine, I'm going to pick up this part first, the brass part, and I have to determine the alpha angle and the beta angle, which I'll talk about in a second, but then I also have to determine the size and the thickness. So the size and the thickness I can come up with just by measuring. So I'm going to grab this thing, like I said before, kind of around the collar here. And so its thickness is 13.6 millimeters. And then its size is 101 millimeters. So I've taken those measurements. And then the alpha angle and the beta angle for this thing, well, if I go back here, this part has the same sort of orientation topography or topology as a bolt, right? Because I've got to orient it so that basically this side is facing upwards towards the O-ring, which is coming downwards. And if I rotated it around so that this side, the gasket side, we're facing the O-ring, then obviously you couldn't put the O-ring on, right? So this is going to be, at least for purposes of grasping for O-ring insertion, a alpha equals 360 and a beta equals 0 are going to be my symmetry angles there. So here's how I use the chart. So I've got a one-handed manipulation process. I can pick up that part with one hand. It's not really like greasy or hot or sharp or slippery, so I'm going to deem it to be a part that's easy to grasp. I know that the part has a thickness of, I think it was like 13 millimeters. So its thickness is definitely greater than 2 millimeters. So I'm over here kind of in the far right-hand side or far left-hand side of the options. And then the overall size was 101 millimeters. So it's definitely bigger than 15 millimeters. So I'm then in this column. And then for the rows, remember I'm a alpha equals 360 and a beta equals 0. So I sum them together and I get 360. Well, this first row is for anything less than 360, a sum less than 360. Here it's a sum of 360 to up to less than 450. And then this one is from equals to 450 to less than 720. And then the last one is equal to 720. So I'm here because I've got 360. And so then what I do is I look at this column and I read over in this column and I read down in this row, and where the row and the column cross each other, that's where I'm at. That's the time for that particular step. So in this case, it's 1.5 seconds. Now, the thing that I didn't explain was what is this HI code thing? So if you look, there are numbers sort of above those times. So 0, 1, 2, 3, 4, and so forth in terms of the columns, and then also 0, 1, 2, 3, and so forth in terms of the rows. So it turns out that this chart is set up so that each one of these individual cells has a 2-digit code that uniquely represents it. So this process happens to be a 1,0 process. And when you represent it, you actually represent it like this in parentheses with the row number first and the column number second. And what that does is it allows somebody that is looking at your analysis to figure out exactly where you were on the Boothroyd and Dewhurst charts to be able to sort of determine what your thought process was. So a 1,0 process is a 1.5 second process. And so I put 1,0 here in my HI code, and then the process time is 1.5 seconds. Now, this justification column is if you don't have to use this all the time, but if there is something sort of unusual or unexpected that happened that might have influenced the way that you did the calculation, you should put it there just to help whoever's looking at your work understand your thought process. So in this case, remember we used the smallest shaft outer diameter as our thickness rather than, right? So that's this picture. I use this as a thickness rather than the diameter all the way across the section that attaches to the hose. And that's because for me, it's very natural to pick this part up right there. And so that's what I use as the thickness. Okay. This is the second process, but I'm kind of over time. So let me just pause there and ask if anyone has questions about how I came up with this number. Okay, I think everybody's good. Okay, okay, yay, I'm getting a thumbs up. Awesome. So I won't do the second process. I'll just mention that you're always going to have 2 handling processes, and then you're going to go from 2 handling processes to insertion, and then handling and insertion, and handling and insertion, and you'll follow that pattern of HI all the way down, typically until you have the part or the assembly fully assembled, and you'll have all these different process times for each of those individual steps. You'll sum them up and you'll get a total time. So that's how you come up with that value. And then that can be used, for example, to estimate the time to manufacture one product, and then take that, multiply that over the number of products that you have to produce. And that gives you a total time to assemble all of the products needed to finish a particular order, which will then allow you to estimate the labor time and hence the labor cost. And that's how you can put the labor cost to do the assembly into the cost for that part that you give to your customer. So that's how that works. Okay, so let me stop there. I'm happy to answer any questions if you guys have them. Okay, looks like no. So that's my last slide. Oh, hang on. There's a couple of questions in chat. Oh, okay. Just somebody commenting no questions, and then a time. Oh wow. Okay. Yeah, no, that's right. It looks like about 6 minutes, which is fine. We've had some really long reassemblies as well, so I'll put that into the data. Yeah, yeah. No, I got you. The O-rings are really hard to deal with. And that's sort of another thing, right? Is you probably in the real world wouldn't assemble this by hand the way that I've asked you guys to do it. You would have some sort of tool that would actually like expand the O-ring, and you'd be able to just insert the part and then snap the O-ring right in place. So this is probably going to end up being like a overestimate of the assembly time, because we really don't have the proper tools to put some of those O-rings on. So not surprising that you got such a long time, because the O-rings are kind of finicky to deal with. So great. Okay. So any final questions before we wrap up? No. Okay. So thanks for sticking around. I'll stop sharing my screen and stop the recording. Maybe. There we go.